Today I'm going to be talking about chasing channel sands, and I'm going to be using various examples, case studies from the Miocene, dominantly siliciclastics in Southeast Asia. Why chase channel sands? Well, they are very frequently sweet spots or productive fairways in our reservoirs. That's due to them being deposited in high energy settings, tending to have coarser and better sorted grains, there being less clay, and of course that all leads to improved porosities and permeabilities. However, it gets tricky when you think about their geometry, because their elongate, often shoestring geometries tends to make them a little bit difficult to track in the subsurface. We see channels in all sorts of different settings. We see them down there in on the right-hand side in deep water settings. We see them on the shelf. They become very prominent in coastal and deltaic settings. And of course you get nicely developed channel sequence in fluvial and alluvial settings. And in fact that's going to very much set up the framework for this lecture. I'm going to look at applications of electrical imagery in deep water settings, then move to a delta front case study, get on top of the delta as it were, and look at some more applications and wrap up with a case study from a tidal embayment. And I'm going to try and follow a theme. I'm going to be looking at outcrops, trying to integrate geological, petrophysical and seismic data, and to show how these applications can be used to develop exploration plays, as well as to evolve depositional models when we're looking at our reservoir and field development planning. Let's start with a deep water application from the Mount Messenger Formation. This was our first work in trying to get into the deep water out in the Far East. A consortium was set up with the Institute of Geological and Nuclear Sciences in New Zealand, several universities and other contributors. And we like this area particularly because of the really excellent outcrops that you have along the coastline, but also the road cuttings and a railway cutting and rivers crossing the area, which give you some really excellent exposure and allow you to put together a good understanding of the depositional model. And on that raised platform, you can see a rig. We actually used the opportunity to drill a couple of shallow boreholes just back from the cliff. So not only did we have our three-dimensional picture from the outcrops, but some well control as well, and we could tie everything together. Let's look at one of those outcrops. In the bottom left-hand corner, we have Peter King, one of the leaders of the consortium. And he's showing the scale. He's also standing in a unit where the beds are relatively low angle and very fine-grained. And we can see above that a sharp erosive base with some pebbly conglomerates along that base. And above the base, we can see the beds are somewhat steeper dipping in the coarser material, dipping down towards the center of the channel unit. And as the channel fills, we can see the sands are getting flatter and flatter and lower angle. And that's very indicative of, as you can see there, a channelized unit. And the flow direction would be out of that surface in the direction of where I'm speaking from. We ran electrical image logs in those wells. And you're seeing an idea of the tool. All the different service companies have tools which make these resistivity images. And let me just talk a little bit about the presentation that we're looking at. When you're drilling through formations which are perfectly flat and the borehole is perfectly vertical, the different bedding surfaces give you slight resistivity anomalies along the borehole wall, and that gives you that image. The lighter colours are more resistive, the darker colours are more conductive. As I say, if the beds are perfectly flat, you'll see a perfectly flat horizon cutting the borehole image. However, as the beds start to dip and the borehole starts to get deviated, you will see that plane changes in angle, and that manifests itself as a sinusoid on the image. And as you go across from north to east to south to west to north, you see the sinusoid, and the amplitude of the sinusoid gives you an idea of the dip angle, and the phase shift gives you an idea of which direction that sinusoid is dipping, which way that bed is dipping. So let's look from that planar surface cutting across the borehole. Let's look at the actual image in the well, and you can see a series of sinusoids over there. You can see those lower angle beds at the bottom in the dark conductive colours. Those are the shales, and above there you have some sand units, and we can see on the dip track the head of those what we call tadpoles are giving you the dip magnitude, and the tail is always pointing down dip. And we can see that the down dip direction is pointing towards the northwest, and as I showed you in the outcrop, that's telling us that the channel axis is in the northwesterly direction, and again we can understand that and interpret that in terms of the actual axial trend of that channel is southwest to northeast. So by looking at the images, by looking at the dips, by thinking about what the outcrop geometries are doing, we can look at the channel and we can see its orientation. So let's go from our theoretical model based on our field outcrop observations and that test well to a real discovery in Southeast Asia in deep water. We can see there some nice stacked channel units, sand units, Baum A and B. They're very bright because it's all been gas charged. This was a discovery. And we can see that there are dips heading off there to the east-northeast, suggesting that with that sharp erosive base that we're looking at a channel units that are stacked, and that channel sand is thickening up a little bit in that east-northeasterly direction, and it's oriented with an axial trend south-southeast to north-northwest. So let's move now a little bit towards the coastline. Let's look at a deltaic, a distal setting. We're now in the South Sumatra Basin, just to the southwest of the Sunda Shelf. And this was an interesting prospect which had already had 3 wells drilled on the structure, but none of them looked terribly attractive. And we'll talk about what would you do next. Would you drill a 4th exploration well on a structure that looked very non-commercial, or would you just move on? Well, this is, you'll see how we built up a paleogeographic model in this case study from our image and log data, and the decision that we made and its outcome. So we know we were in a deltaic setting. We know that deltas prograde out into the basin, and we also know that the most distal parts are the finest grain sediments, and as you come up onto the delta, the sands become coarser and coarser till you end up with some really very good reservoir potential sands on the top with your distributary mouth bars and the fluvial setting. Let's go to Bengkulu, which is in South Sumatra, on a field trip, and let's look at that coarsening up sequence at outcrops. And you can see there, slide 1, 2, and 3. Let's visit outcrops that show you nicely the Prodelta slope sediments, the coarsening up as one mows through the lower to the shore face faces until the upper shore face and the distributary channels at the top. Here's the bottom of the sequence, and it's dominantly very fine-grained sediments, but we have a very nice, good quality sand in there. We believe that that is a storm deposit that's been washed off the top of the delta during a typhoon episode, and the sands have been washed and slurried into deeper water. But otherwise, it's dominantly fine-grained. We move up the sequence, and now we get into the coarsening up unit with mudstones overlain by siltstones and then some fine stands. And around another corner, as we walk up and move up the sequence, we're going to be seeing the delta top. And as you can see here, the sands are very coarse. You can even see pebbles in here, and this is remarkably good reservoir potential right at the top of the unit. So let's look at our images, and the first well, unfortunately, was lost when it reached TD. We had absolutely no data in there, apart from the cuttings logs indicating there was some sand and there were some shows. In the other two wells, we had a whole series of images suggesting a very distal setting. In other words, we were looking way out on the shelf. The unit we're looking at there is about 10 foot, 3 meters thick. There's just a little bit of sand. As I say, there were some oil shows, but in general, very, very little in the way of reservoir potential. We were simply too far out into the basin to represent and have manifested any good reservoir facies. This is a nice little sand. This is one of those scoured surfaces, one of those storm deposits. And even though the reservoir quality is beautiful, you've only got 2 or 3 feet of potential reservoir. So one's inclination is to walk away from the structures. Here's the regional play content. The sands were being washed in from the northeast. Those were the 3 well locations. We've definitely got a kitchen there. There's a mature basin with regards to the source rocks. The hydrocarbon is clearly migrating into the structure, but the reservoir just isn't there. And you could say, well, let's move towards the course of the sands, which is a very intelligent thing to do. But you would move in a northeasterly direction, and by the time you've moved 2 or 3 kilometers, you're going to be outside the 4-way closure. So once you start to get good reservoir, you're going to be out of the zone where you're going to get a trap. So I think most people would look at that, scratch their heads, be rather disappointed, and move on. However, we noticed something very, very different. Instead of the palaeocurrent directions in all of those various sands consistently pointing down towards the southwest, we noticed an awful lot of current being pushed along parallel to the coastline. So in fact, the main sedimentary trend seemed to be from the southeast up towards the northwest. And that, of course, put a completely different perspective on the whole prospect. David Desiltals, my co-author, put some more maps together and showed that the sands were indeed coming from the northeast, but were being then moved along the coastline. And this has a big significance because if one's ready to, move to the northeast, you quickly drop out of a closure when you're looking for your better reservoirs. But with this palaeocurrent trend, you could actually expect to move 6, 7, 8 kilometers towards the east-southeast, and there's a much, much better chance of catching good sands in a more proximal setting. So we drilled up on the eastern side of the structure. Originally that hadn't been attempted because it was very thick rainforest and a lot of swamps and a lot of access problems, but these were then overcome to drill that 4th well, and it was remarkably successful. We ran into 8 or 10 thick channel units, 50 to 80 foot in thickness, and I've picked some dips there to show you the palaeocurrent direction. And as very much as you have in the Barron Delta, up in Sarawak, you have the river system swinging and the sands being developed along the coastline. Something very, very similar happened here, and we've got some excellent sands being developed within closure. You can see the nice sharp base of the sand unit. You can see the cylindrical character of the channel. You can see those beautifully developed faucet beds. When you look closer at the images, you find it actually quite difficult to match bedding surfaces all the way around the borehole, and that's because those are trough crossbeds. They're poor planarity along those bedding surfaces, very much indicative of high current regimes. What eventually happened with this play? Well, that field has now been developed, and from what looked a very shaky prospect, with 3 very marginal wells, we now have 35 producing oil wells on that structure. I'd like to now move further up on the top of the delta and look at a case study from Kalimantan. This is the Mutiara field, and after the study I'm going to be talking about it. It was given a new classification and renamed the Barras field. It's a northeast plunging anticline. It's a surface feature. You can actually see the trap from location. The production started in the 1970s. The field produced extremely well, but when infill drilling was done in the late 80s and the early 90s, there were a lot of nasty surprises. The whole field was put under a major restudy. I'm going to talk about the case study, and as a consequence of that case study, some pools of new oil in an old field were found in the order of 100 million barrels at a couple of different reservoir levels. And as you can imagine, the economics of that amount of oil, when your surface facilities are already completed and everything's been done to develop the field over many years, you can imagine the economics are extremely attractive indeed. So this is a cross-section across one of the study sands that we looked at here. We're looking at the well separation being about 1 kilometre in each case. And that cross-section, I'll show it later in a following slide, cuts approximately from the south up to the north across that unit. And on the left-hand side, you see the sand is completely shaled out. There's a well with a little bit of gas in it. Then the sand has water. It has oil in the next well. 3 more wells where it's simply water-bearing. And over on the northern extremity, we see that the whole thing is shaled out again. The original correlations were done very lithostratigraphically, simply matching sand with sand with sand. And that was because people believed that the sands were thick and continuous, and that we were looking at a very conventional anticlinal structural play. However, when the rework was done, and people focused on, first of all, correlating the high and the low gamma ray coals, and then seeing where the sands fitted in afterwards, we were clearly looking at a very heterogeneous sequence of sands. And one immediately is driven to think of, well, the present-day Mahakam Delta with lots of channels, and we're probably looking now at a series of channel units cutting across that anticline. This is the seismic that was shot, high-resolution 2D seismic, after the wells were driven. And you will see in there the test sand in the center on that well. And as you look at the reflectors, you'll see how those coals are being nicely picked up across the area. And you will also see that between the coals, there's quite a bit of variation of the reflectivity, the strength of the reflectivity within the units. In other words, something is going on with the seismic attributes. So across that test sand, that E314 to E315 unit, seismic attributes were extracted and maps were created. Unfortunately, it's very difficult to look at those seismic attributes and suddenly understand why some of the wells were dry and some of the wells had oil, and in other wells the sands were missing altogether. Because, you know, we can put together a good mathematical representation of what we mean by the RMS amplitudes and the average trough values, but what does that mean geologically? The seismic was shot through the wells. So in the wells themselves, we have good petrophysical parameters, attributes, which we can understand, but we can't map. Whereas between the wells, we've got the seismic attributes, which we can map, but we don't know what they really mean. So the key is to try and calibrate the maps with the hard petrophysical data, And then a very interesting model starts to come out. Here is one of those attributes and how it matches the net sand percentages in the well. And you can see that when there's lots of sand, that average value of the trough has got a low value. Where there's little sand, it increases. And there's a very good statistical relationship, between the attribute and the amount of sand. So that whole attribute map can be recast as a thickness map. And one can see there the yellow and the green colours are our sands between 80 and 120 feet thick. And the purple and the browns are the shales. And as I say, our cross-section was cutting that unit from the south up towards the north. And we're looking at a combination stratigraphic structural trap with the oil pool, on the southern southwestern limb of that unit. Now, I've just talked a lot of geostatistics, haven't I? I haven't put any geological realism into that picture. And something else I should have stressed was that, in fact, there was only out of 280 possible matches between the petrophysics and the attributes, only about half a dozen suggested a good, viable trend. So it makes one worry a little bit about whether we're just fantasizing with the geostatistics or there's something real there. In parallel with this petrophysical and geophysical work, I myself had just moved into Jakarta, and I'd been looking at the geology from the images and the dips, and independent of the workers, Rupa Gear and Arifu Bowo, who'd been coming up with the seismic guided maps, I'd come up with a geological map, not even knowing, in fact, they were working on the same project. And this was the sketch cartoon map, which I came up with, showing a channel unit sweeping across from the west to the east with the banks of the channel either side. So you can see that using two very different approaches by different people, in fact it turned out in different buildings in Jakarta, we ended up with a very, very similar model. And that gave us a lot of confidence to move ahead and to pick some well locations. A couple of wells were drilled. In one of them, we predicted just under 100 feet of sand, and we came in with almost 110 feet, completely full of oil, of course. And the other sand we'd predicted just over 100, and that came in pretty much bang on 100 feet of sand. That gave us a lot of confidence to tighten up the mapping, and you can now see after 4 wells have been drilled, additional wells in that pool of sand, you can see the channelized unit sweeping across from the west to the east. You can see the structure plunging down to the northeast and giving us that combination structural stratigraphic trap up on the southwestern part of the structure, a little bit of a gas cap, a nice oil pool, and a couple more wells were drilled in there. And I've put on there that first cross-section which I showed you, which went from the muds into the tiny little gas cap, into the water zone, back into the oil leg, and then cut through the water zone to the other side of the channelized unit. So the whole story fits together now and makes a lot of sense. As I say, a couple more wells were drilled. This is what the images look like in those wells. You're seeing the dips indicating some fill at the very bottom of the channel in the sands above the clay base. And as you move up the sands a small amount, you see some very nice cross beds. You can see that these are moderate energy planar, good continuity of the sinusoids right across the images, and that dominant east-southeasterly trend predicted from the channelized direction. This study was done with a lot of outcrop work again, looking at the Mahakam Delta as a current day analog, in addition to integrating the seismic and the geological and petrophysical data. And I'd say the highlight here is that to discover, 20 years into production, new oil in an old field, when all of your production facility costs are already in place, gives you a very, very attractive financial payback, payout for the work that's and the additional wells that have been drilled. My last case study, I'd like to look at a tidal embayment, very much as you have in the Malay Basin area. Again, it's an example from the Miocene. And this is from the joint development area between Thailand and Malaysia. And what was fascinating in this example is that the well over on the west-southwest, which seems to have a stronger seismic anomaly, was water, wet, the reservoir. There was no hydrocarbons at all. But the other well, which is lying a little bit away from that attribute, on the more easterly side of the block, actually had some very, very good gas, which produced on test. So you'd actually probably expect it the other way around. So what's going on here? Well, let's look at the images again. You can see there's a sharp, erosive base. You can see some debris over the base of the channel. And as you move up into the channel unit, it was about 7 or 8 meters thick, you start to see some nice bedding. You see a bimodal characteristic of the bedding surfaces. You see clay drapes, you see wavy beddings, you see flazers, you see biotubation, you see all the characteristics of a channelized unit. So we'd be looking at a setting very much like something like this over here. The next step was to go back to the drawing board quite literally and redo the correlations. The correlations were very good. They were always within about 5 to 10 meters of where the recorrelated sequence was, but we were able to bring in an additional dimension of sequence stratigraphy here and break out the units, repick the attributes, and the reinterpretation suggested that those two sands were in different channelized units, but were in fact not a contiguous single system, but there was actually a sedimentary break, a stratigraphic break between the lower gas-bearing sand, which now turns out to be enclosure when you map that channelized unit, and the slightly higher in the sequence sand, which now turns out in fact not to be inside structural or stratigraphic closure. So it suddenly explains why that upper sand has only water in there, but why the lower sand, which probably extends up towards the north, in fact had gas. So the ability to use the images not only to recognize the channels, but also to help with your correlation and correlate from well to well and recognize sequence boundaries was extremely helpful in breaking this open, looking at the individual hydraulic units, optimizing what we were getting out of the seismic attributes, and coming up with a good reservoir model. So what I've tried to do, in the last half hour, is to talk about the sedimentary features that we see, to look at the erosional bases, those scoured erosional bases of our channel units, the presence of foreset beds, which could be either tabular or trough, which is a good indicator of depositional energy. I've shown you uni and bimodal palaeocurrent directions, and I've also shown you the effects of fine laminations and biotubation, which can become very important when we're looking at our relationships between porosities and permeabilities, and understanding, again, the quality of our different hydraulic units. And I've also tried to pick things in a series of different depositional settings. We started off in New Zealand with the deep water feeder channels. We then moved into the South Sumatra Basin and looked at delta fronts. We came across into the Kutai Basin and looked at delta top systems, and then across into the Malay Basin and looked at tidal channels. And I selected all the examples, as I said, from Miocene reservoirs. In terms of the business model, we started up trying to develop an exploration concept to help us get a better control on what we were doing, for example, in the deep water. We've looked at how appraisal drilling programs can be helped. In other words, if you've got a couple of not attractive looking wells, how you can go back to your plans, go back to your geographic models and try and see which direction sands can be improving. We changed in the production field, we changed the model so much that they changed the name of the field. And that was a very good example of how you can integrate all of your data, again come up with different geographical, paleogeographic models and turn something from a structural into a stratigraphic play and find new oil in the process. And finally, another example of integrating your sedimentology with your logs, with your images, with your seismics to get a much more robust sequence stratigraphic framework of your different hydraulic units and to allow that to push that into your field development planning and understand where to land and how to land your future wells. So I hope you've enjoyed that. I had a lot of fun working with my co-authors. I'd like to recognize them again. David de Soutels with Santa Fe, Bob Koch, who is with Vico in Indonesia, and Amarudin Mohammed Zain with Petronas, and the various companies which allowed us to present this data. And thank you again.